If you follow developments in science, you've probably heard of gravitational waves, which were first detected directly in 2015. But what are they, and why should you care? I'm astronomer and author Jeffrey Bennett, and I've created this video to help you answer these questions. Let's start with the short answer. Gravitational waves are an important prediction of Einstein's general theory of relativity, which changed the way we understand space, time, and gravity, and therefore fundamentally changed our perception of how we fit into the universe, both as individuals and as a species. You should therefore care about their detection for at least two reasons. Scientifically, it confirms Einstein's important scientific work. Perhaps more important, the technological challenges that had to be overcome to detect gravitational waves represent a remarkable demonstration of what we can achieve when we put our minds to constructive rather than destructive purposes. With that short answer in mind, let's look in a little more detail at exactly what gravitational waves are and how they were detected. You may recall that Newton discovered the universal law of gravitation, which tells us that every object in the universe attracts every other object through the force that we call gravity. Newton even gave us a simple formula for calculating the force of gravity, which we won't go over here, but you may have learned about elsewhere. However, Newton did not know how the force of gravity was transmitted between objects, and in fact, he found the entire idea of a gravitational force that could act between objects separated by great distances to be very mysterious. This mystery was finally resolved more than 2 centuries later by Einstein when he published his general theory of relativity in 1915. In Einstein's view, gravity arises from curvature of what we call space-time, which you can think of as being somewhat like a fabric to the universe. In this view, space-time is curved by masses in much the same way that heavy weights curve a taut rubber sheet, except in 2 more dimensions. General relativity thereby gives us a new way to think about orbits. For example, instead of thinking of planets orbiting the Sun because the Sun somehow magically acts on them from a distance, we instead think of the Sun as creating a bowl-shaped depression in space-time, and orbits simply follow the natural contours of this depression. Moreover, although not shown in this diagram, the orbiting masses must themselves press down on the rubber sheet. Animating the analogy, a planet orbiting the Sun must make a small depression in the rubber sheet that moves with the planet. Much like swirling your finger in a pond, this moving mass should generate ripples moving outward across the rubber sheet. These ripples are what Einstein identified as gravitational waves. However, the equations of general relativity show these waves to be so weak that Einstein himself doubted we'd ever be able to detect them or notice their effects. But Einstein not only underestimated our technological advance, he also didn't know about objects like neutron stars and black holes, which can generate much stronger gravitational waves. This next animation shows a rubber sheet analogy for a binary neutron star system in which 2 neutron stars are orbiting very close to one another. The ripples represent the gravitational waves, and as the animation tries to show, these waves carry energy away from the system. Because energy must be conserved, the energy carried away from the system must come at the expense of the system's orbital energy, and this should cause the orbits to gradually decay. In other words, the orbital period of the binary neutron star should gradually shorten in a way that can be precisely predicted by the equations of general relativity. In fact, this is how astronomers first discovered strong evidence that gravitational waves really exist. This graph shows data for the first discovered neutron star binary. The red curve shows the orbital decay predicted by Einstein's equations, and the dots are actual data points. The near-perfect match tells us that the system really is losing energy to gravitational waves, an idea that has been confirmed by the discovery of several similar systems that show the same type of evidence. However, strong as this evidence is, it is still indirect. To detect gravitational waves directly, scientists realized that they need both a stronger signal and an extremely sensitive detector. The key to finding this stronger signal comes from looking at the trend on the graph. Notice that the orbital decay accelerates with time, which means the 2 neutron stars must eventually spiral into each other. This won't occur for many millions of years for the system shown here, But simple estimates suggested that mergers of neutron stars, or black holes, must occur somewhere in the universe at least a few times a year. This next animation shows the accelerating decay of the orbits as the emitted gravitational waves strengthen. Moreover, the final merger of the neutron stars should emit a particularly strong pulse of gravitational waves. The same type of pulse can come from the merger of two orbiting black holes. Both have now been detected. The instrument that first detected gravitational waves is called LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. This aerial view shows the LIGO detector in Hanford, Washington. Notice the two arms arranged in an L shape, each 4 kilometers long. According to general relativity, this arrangement should mean that as a gravitational wave passes by, one arm should very slightly shorten while the other slightly lengthens. This animation shows the idea, with the red lines indicating the laser light that is used to measure extremely tiny changes in the lengths of the arms. In fact, LIGO is so sensitive that it can measure changes in length that are far smaller than the size of a proton. With such tiny changes in length, you might wonder how scientists could ever be confident that a signal was real and not an artifact of some local event. The answer is that LIGO has a second detector, located in Livingston, Louisiana, so scientists can be confident a signal is real if both detectors record the same signal. Because relativity predicts that gravitational waves should travel at the speed of light, one detector should receive a passing signal slightly before the other. This graph shows the first such detection, made in 2015. Notice the match between the signal received at the Hanford and Livingston detectors. Using the equations of general relativity, scientists were able to conclude that this signal came from the merger of two black holes in a galaxy about 1.3 billion light-years away. Gravitational waves are fundamentally different from any form of light, and they therefore give us an entirely new way to study the universe, and scientists expect rapid progress in their study. Already, LIGO has been joined by a third detector called Virgo, which is located in Italy. Just shortly after Virgo came online in 2017, the three observatories detected the first unambiguous gravitational wave signal from the merger of two neutron stars in a galaxy about 130 million light-years away. Moreover, having three detectors allowed scientists to pinpoint the location of the neutron star merger well enough for follow-up observations in light across the spectrum, from radio waves through gamma rays. These early successes of gravitational wave astronomy are spurring new technological developments that should further improve our capabilities, and you should watch the news to learn of the many gravitational wave discoveries sure to come in the future. I hope you found this video useful. If you'd like to learn more about relativity and gravitational waves, I encourage you to read my book, What is Relativity?, published by Columbia University Press, or my astronomy textbook, The Cosmic Perspective, published by Pearson. If you choose the latter, be sure to order it with access to Mastering Astronomy, where you will find dozens of other videos that I've made on astronomical topics, along with many other study resources. You may also wish to visit my blog at jeffreybennett.com/blog and follow me on Twitter @JeffreyOBennett. Thank you for your time in watching this video.